Hello, everyone. I'm Yosuke Kaneko, and I'm the current chair of the IPNSIG. Today, it's my honor to welcome Vint Cerf to deliver a talk on the DTN overview here at the IPNSIG Academy. Vint is Vice President and Chief Internet Evangelist for Google. He's the co-designer of the TCP/IP protocols and the architecture of the Internet. He has served in executive positions at ICANN, the Internet Society, MCI, the Corporation for National Research Initiatives, and the Defense Advanced Research Project Agency. Also a former member of the U.S. National Science Board, he's the past president of the Association for Computing Machinery and serves in advisory capacities at NIST, DOE, NSF, and NASA. He's a visiting scientist at JPL and also a board member of the IPNSIG. Vint is a recipient of numerous awards, but I will let you all do a Google search on that so that you will get to know more about his great achievements. And now I would like to invite Vint to start his presentation, but please, if you have any questions, please make sure you provide them in the Q&A box so that we can address them later on. Okay, so with that, Vint, the floor is yours.
Thanks so much, Kaneko. I really appreciate the opportunity to introduce this topic. Let me say, first of all, that this is a very light overview. We're not going to dive terribly deep into the details of the bundle protocols. You'll find that the rest of the Academy lectures get into some detail, which will give you much clearer understanding of how things actually work. But this is intended simply to introduce the concepts to you. So let's go to the first point, which is that we are interested at the Interplanetary Network Special Interest Group, now the Interplanetary Networking chapter of the Internet Society, in the design, construction, and use of a solar system-wide Internet. And this lecture is to give you a sense for where this concept came from and where we think it is headed. So let me take you back in time. Some of you will recall that the Americans attempted to make a landing on Mars successfully in 1976 with two landers called Viking 1 and Viking 2. In the, I think it was in July of 1976, which all seems very appropriate because we were celebrating an important anniversary. But then for 20 years, from 76 to 1997, nothing seemed to work. All of the various attempts, whether it was American or otherwise, seemed not to be successful. And then in 1997, the Pathfinder project landed a small rover on Mars. And as a result, the Sojourner mission landed this, the Pathfinder mission landed the Sojourner robot on Mars successfully, and that was cause for great celebration, the first time that we'd been successful in 20 years. There have been subsequent missions, which I'll talk about in the next few slides. But the important thing is that it triggered, this 1997 landing triggered a visit to the Jet Propulsion Laboratory to meet with the team that was doing the communications for the Pathfinder mission. And in the course of our conversations in 1998 in the spring, we reached the conclusion that we should be seriously thinking about the design of an interplanetary backbone communication network that we would likely need 25 years hence. And that we assumed it would take some time to both develop the concepts and the details and then implement and test before we actually got off the planet, and needed this capability in a serious way. So we began in 1998 with the design of an interplanetary backbone network. We started out thinking that we could use the TCP/IP protocols that had worked quite well on planet Earth. As many of you will know, that design began in 1973. The internet was turned on operationally in 1983. And by 1993, the World Wide Web had shown up, and of course, an explosive growth followed. But we started looking at Mars, and we thought, well, this should work okay on Mars. It worked okay on Earth. Then we did the math, and we realized that the speed of light was too slow, no thanks to Dr. Einstein. When Mars and Earth are closest together in their respective orbits, they're still 35 million miles apart. And the speed of light at 186,000 miles a second is so slow that it takes 3.5 minutes for a radio signal or a laser to propagate between Earth and Mars. And when we're farthest apart, it's 235 million miles. It takes 20 minutes one way for that signal to propagate, and of course, another 20 minutes for any response to come back. I can tell you that the TCP/IP flow control system, which is quite simple, you basically send a message to the other guy saying, I've run out of room, don't send anymore. Except in this case, it takes 20 minutes for that signal to get to Mars. And the meanwhile, your communicating partner is pumping data at you at full speed. And of course, you can't receive it and it falls on the floor and disappears. So flow control doesn't work. And then we looked at the domain name system and imagined the scenario. You're on Mars, you want to get in contact with something on Earth, so you have to do a domain name lookup to get the IP address. 40 minutes later, you get an IP address, which turns out to be wrong because whatever it was that you wanted to communicate with was in motion on Earth and has a different IP address because it moved into a different network domain in between the time that you asked for the IP address. So DNS doesn't work either. The result after we realized these parametric differences was to start thinking more seriously about delay and disruption tolerant networking, a kind of networking in which the parametric space is much more extreme than it was in the course of the development of the original internet design. So we called the protocol that we developed the bundle protocol to make it sound kind of like packets, which in fact it is. In fact, the analogy between the bundle protocol and the internet protocol is fairly similar. Both of them are not reliable transmission systems, and if you need reliability, you have to build that on top or below the bundle layer. In terms of naming, unlike the hierarchical IP addressing scheme in the bundle system, the scheme is essentially flat. It's a big string of numbers. And at each hop, a lookup has to happen to decide where you're going to send the bundle in the next network or through the next relay. There's still some arguments about how well that's going to scale. And so those of you who are wondering whether everything is all done, the answer is no. There's still plenty of opportunity to refine the bundle protocol suite, although it has gone quite a long ways towards standardization since its original implementation. We also discovered very quickly that one of the mainstays of network management historically has been low latency interactions with target routers, for instance, that are under control. In the interplanetary system, of course, latency is not your friend. Ping is not your friend because you don't know how long it's going to be after sending a ping packet that you're going to get an answer back. And so we've had to develop a different philosophy of network management where the target router that's theoretically under control is essentially running autonomously based on advice given to it by the network management system. But there can't be a lot of handshaking back and forth because it's A, not reliable, and B, it's too slow from the latency point of view. Finally, I can recall in that meeting, or certainly in a subsequent one, standing up in front of the whiteboard saying to my colleagues, one thing that we want to avoid is a headline that says 15-year-old takes over MarsNet. Because too often we were seeing that kind of headline in terrestrial implementations of the internet. So we decided we would incorporate strong authentication and encryption into the architecture from the get-go, having learned lessons from our experiences with the TCP/IP protocol suite. We began very early on to work with two different organizations to standardize the protocols. The Consultative Committee on Space Data Systems, which is made up of the spacefaring nations of the world, is where the original standardization effort began. And then in parallel, we started working with the Internet Research Task Force to introduce the delay and disruption tolerant networking concepts to the engineers who are part of both the Internet Engineering Task Force and the Internet Research Task Force. And then we moved the resulting work in the IRTF over to the IETF for full up standardization. And I'm pleased to say that Bundle Protocol version 7 has just been standardized and voted out, so to speak, from the Internet Engineering Steering Group. So we've been pursuing this goal now since 1998, and we're at the point now where a number of implementations have been made. So the interesting thing that happened in 2004 is that the Spirit and Opportunity landers arrived in January of that year, almost simultaneously. And the intent was to transmit data back from the surface of Earth to the Deep Space Network. And so this group that you see at the top bullet here began the prototyping work on the interplanetary protocols. And when Spirit and Opportunity landed, the original plan was to transmit data back to the Deep Space Net at 28.5 kilobits a second. The Deep Space Network is made up of 70-meter dishes in 3 places around the Earth, in Madrid, Spain, Canberra, Australia, and Goldstone, California. And so these huge 210-foot dish antennas can stare out into the solar system and have significant antenna gain because of their size. So weak signals get amplified significantly. So the original plan was to transmit data directly from the rovers, the Spirit and Opportunity, to the Deep Space Net. It turned out the radios overheated or something went awry, and it forced everyone to back off the duty cycle to protect both the radios and also the other instruments on board, at which point the scientists became very grumpy because 28 kilobits was bad enough. Now we have a reduced duty cycle and less data would come back. But one of the JPL engineers reminded us that there was an X-band radio on the rovers, and that we had sent orbiters 2 years before that to map the surface of Mars to decide where the rover should go, and that the orbiters also had an X-band radio, and they also had programmable capability, and they had power from their solar panels. And so the idea was to send prototype software, which had already been space qualified, called the CCSDS File Delivery Protocol, to essentially install that capability both on the Spirit and Opportunity rovers and on the orbiters. And as a consequence, we made use of the fact we could hold the data in the rover that had been collected. And when the orbiter came overhead, we could squirt the data up to the orbiter at 128 kilobits a second, because the distance was much shorter than all the way back to Earth. And then the orbiter would hold on to the data until it got to the right place in its orbit to transmit data back to the Deep Space Net. And because it was outside of Mars' atmosphere, it was able to transmit the data at 128 kilobits a second. So we got 4 times the data rate by using store and forward techniques, which gave us a great deal of, I would say, confidence that the more elaborate bundle-based protocol design would also work well to serve our communication needs. In this particular case, the file delivery protocol was staged in a manual way, although the bundle protocols would do this in a purely automatic fashion. A couple of things to point out about the difference between the bundle protocol suite and the TCP/IP protocol suite. One thing is that in the bundle protocol, unlike the internet, if you go to an intermediate node and the node does not have connectivity to the next hop, you hold on to the data in the network. This is not something we did with the internet, because when we were designing it in 1973, memory was expensive, and an end-to-end retransmission didn't involve very much delay, because we were talking a few seconds at worst, so, or even maybe 500 milliseconds. So in the interplanetary case, though, imagine that you're trying to transmit data to, let's say, Jupiter or maybe Titan or something. You're transmitting data and it gets to the Mars relay. If the Mars relay cannot see the destination node around Titan, instead of throwing the data away, it holds onto it in the network at the router. And that's not something we do in the internet. But you can imagine it makes no sense to throw the data that you worked so hard to get to Mars away before and then have to retransmit it all the way back. In fact, the value of the bundle protocol is that it works even if you do not have continuous connectivity from the source to the destination, unlike the assumption in the internet design, where it's assumed that all the routers in between are fully connected and the data can be transmitted from source to destination. So we began serious work on the bundle protocols and used our implementations to test on in a variety of circumstances. We were able to get access to the epoxy spacecraft, which the Deep Impact spacecraft, which was part of the epoxy mission, which visited 2 comets. It had completed its mission, and NASA gave us the permission to upload our prototype software in order to test that on the Deep Impact spacecraft. We also have been testing since about 2009 on the International Space Station. We've been providing it with upgrades to our implementations over the 10 to 12 years, or 13 years now, that we've had access to the ISS. The astronauts have been using the bundle protocol for personal communications and other kinds of communications applications, not involving the actual operation of the International Space Station, but the experiments on board, and of course with the astronauts using it for their personal communication. In 2012 through 2016, we also made use of a low latency control of a robot vehicle from the International Space Station down to Germany. I think it was in Heidelberg. So this was sort of like the Sojourner robot that landed on Mars in 1997 and triggered all of this. The latencies are very low between the International Space Station because it's only a couple hundred miles up. And so it's possible to literally steer the robot. That's simulating what it might be like if we had astronauts who were orbiting Mars and directly controlling a robotic vehicle on the surface. We wouldn't do this from Earth because the round trip time latency is too large to be effective. We've also tested at high speed using the LADEE, the Lunar Atmosphere and Dust Environment Explorer spacecraft, which was in orbit around the moon. We had a laser reflector on board, and we were able to test the protocols running at 600 megabits a second, which gave us confidence that the system would work not only at high latencies, but also in low latency, high speed environments. We continued our work, and these are just to give you some additional examples of the things that we've done in order to increase our confidence in the implementations, and also to test various implementations that are based on the standard specifications. So we've been testing, for example, implementations between the Japanese Space Agency, JAXA, which is where Kaneko works, and NASA, using the ION implementation, which is Scott Burley's implementation of the bundle protocols. As I said before, we've been standardizing this in the DTN working group of the IETF. We've also implemented some additional protocols like the Licklider transmission protocol. And I need to pause here and tell you a small anecdote. JCR Licklider was a professor at MIT in the 1960s. He was a psychologist, and he was convinced that computers could be used to augment human capability, not simply to do numerical computations. So he was interested in non-numerical computing. And another gentleman also of that same era, Douglas Engelbart at SRI International, had a similar passion about the use of computers for non-numerical purposes that could augment human intellect. And so the two of them got together in order to support this exploration. And somewhere, if I'm remembering correctly, in 1962, Licklider sent a note to his colleagues about the possibility of networking computers together in order to make use of them in this non-numeric way. And he sent a letter around saying to his colleagues, I want to tell you about my intergalactic network. Of course, that was tongue-in-cheek, and yet we wanted to recognize Licklider's amazing prescience and of course our activity in the development of the interplanetary backbone. So we've named one of the transmission protocols the Licklider Transmission Protocol, or LTP for short. One of the most unusual applications of delay and disruption tolerant networking has been undertaken at Luleå University in the northern part of Sweden for literally the last 13 or 14 years. Maria Uden and Sam Grasek and others have been using delay interruption tolerant networking to track the reindeer that are managed by the Sami, the reindeer herders in the northern part of the Arctic. They're using delay interruption tolerant networking in order to track where they are, so that if at need, of course, the reindeer herders can find any that might be lost. They can keep track of where they are. So for the present, we've been working closely with NASA, with the European Space Agency, the Japanese Space Agency, and the Korean Space Agency on deployment and testing of the protocols. More recently, we've worked very closely with Professor Ronnie Bohl and his students at Utica University on further implementation and test of various implementations of the bundle protocols. We're continuing testing activities with the space agencies. We have source code available, one source code from the Technical University of Braunschweig and another, the ION implementation from NASA. And in addition to that, now that the Interplanetary Network Special Interest Group is in full operation, the project's working group, which is led by Oscar Garcia, who is also a board member, is actively engaged in a number of different experimental practices, testing of implementation, interoperability, testing at scale, an increasing number of nodes of an interplanetary backbone running terrestrially at the moment, although we have eyes on the possibility of using small sats in near-Earth orbit in order to continue to test the protocols in increasingly challenging environments. You'll be hearing from Oscar about the various projects that are underway at the next Academy meeting on July 13th. So our future plans for the moment include the implementation of DTN for the missions to the moon, in particular, the Artemis and Gateway missions that are mounted by the US, as well as parallel missions being undertaken by the Japanese and by the Europeans. The second thing is that in the near term, IPNSIG.org, which is where the Interplanetary Network Special Interest Group has its website, is also looking at near-term terrestrial LEO and cloud-based testing. One thing I'm very pleased to report is that the implementation of ION has been feasible on all three of the major clouds, the Google Cloud, the AWS Cloud, and the Microsoft Azure Cloud. And we have, of course, a number of implementations running in laptops, desktops, and in some cases, mobiles. So there's a proliferation, and I've left out Raspberry Pi and some of the other small computing devices. So the whole point here is that ION and other implementations are becoming available for purposes of testing, experimentation, and deployment. And of course, in the longer term, we're quite excited about the possibility of really building an interplanetary backbone network. And so you'll find in the next slide reference to a report which IPNSIG released last June, looking at a much longer term view of the network. This is where we think we're likely to be in the mid-2030s. And although this looks as if it's overstated, I can tell you that many of these systems are already in operation now. In the middle bottom of the screen, you see something that's labeled DSN with a giant antenna. That's the Deep Space Network. And of course, there are 3 nodes of that. There's the TDRS system and others, the NSN as well. These are all operating systems in the environment, with a few that are still to come. Gateway, for example, is still in the future. And LunaNet over on the left is part of the return to the moon activity. MarsNet is already functioning, at least for those rovers that have landed up until now. We hope, of course, to see an upgrade to the full bundle protocol suite at some point in the future as the need arises. So this is where we think we're likely to be in the 2030s. But looking further out, there's always this question, now that we've done the interplanetary network, what's next? What about interstellar? And for a long time, I was quite excited about this possibility. But there were three major barriers to successful deployment of a mission to Alpha Centauri. The first one is propulsion. The current propulsion systems would take 76,000 years to get to the nearest star. That's kind of a long time for an experiment. And then there's the problem of navigation, because you'd have to do mid-course corrections on your way to something 4.3 light years away. And I can tell you that the typical mid-course correction that takes place in the solar system involves a signal from Earth to the spacecraft to tell it, to do a burn over whatever amount of time is needed. But imagine you have a spacecraft that's already a light year away. It takes a year for the signal to get there to tell it to do anything, and it takes another year to find out what happened. And of course, the farther away it gets, the longer it takes to do that handshake. And so navigation that way is not likely to work very well. Fortunately, there's the possibility of using variable stars, Cepheid variable stars, either in our galaxy or in other galaxies, which are not likely to move very much over the course of, say, 100 or 200 years. And you can use those as a kind of galactic positioning system as opposed to geocentric positioning system. And so that it may be possible that self-navigation is feasible for this mission. And then, of course, the final problem is that if you get there, you have to slow down in order to go into orbit. Otherwise, you might get one picture and go blasting through at 20% the speed of light. The second problem is that in order to communicate back to Earth, you have to be able to aim your antenna correctly. And I want you to think for just a second about what 4.3 light years implies. What it means is that you need to point your antenna where the Earth is going to be 4.3 years later than where you are, than the point at which you're transmitting, or the time at which you're transmitting. So calculating where to aim the antenna is a non-trivial exercise. Well, we went to the Lincoln Laboratory at MIT, which is well known for its engineering expertise, and we said, could you help us quantify how far away we are from being able to mount a successful Alpha Centauri mission? And no, they didn't say you're 4.3 light years away. They actually did a bunch of computations to figure out how far we were away from having enough power, having adequate propulsion. And there is a video of a wonderful lecture given by one of the scientists at Lincoln Labs, and this slide shows what the link is. I'm sorry, I'll tell you what the bottom line was. We're 53 dB away on all metrics, or summed up over all metrics, from being able to mount a successful mission. There's something for future scientists and engineers to do. So I think I'm going to stop there and ask Kaneko if he would like to bring you up to speed on what's coming next, and also to try to moderate any questions that you might have. So Kaneko, over to you.
Yeah, thank you, Vint, for the great presentation. Let's see, we have questions in the Q&A box. The first one is from Siva, and Siva says that the interplanetary internet can't be wired. Hence, you must have paid special attention to all forms of radio, microwave, and other wireless technologies. Are there technologies that allows signals to hop over long and vast distances without bandwidth loss? In other words, IPN work with experimental wireless technologies not yet commercialized on the terrestrial plane.
I wish that I could give you some secret, that we found that overcomes the speed of light delay, but we have not. So whether it's optical or radio, which of course is all electromagnetic radiation, it's just different wavelengths, either any of those EM signals require speed of light delay, or introduce speed of light delay. So we haven't been able to fix that. We have, however, come to the conclusion that optical signals are very, very attractive because of the higher data rate that they can sustain. But keep in mind that the signals lose strength at the square of the distance. So you can imagine the farther away we go, the weaker the signal, and therefore the more power you have to have at the sending antenna, and presumably the higher gain you need at the receiving antenna, which is usually achieved by having a larger, physically larger antenna, or for that matter, a telescope in order to capture a laser signal. The problem with the telescope trick, which is very attractive from the terms of bandwidth, is that the pointing accuracy has to be really, really good in order to get the beam to hit the antenna or hit the telescope at the right place to be received with effectively. So there's still work to be done to perfect aiming capability for laser-based communication. There's a great deal of interest in that. NASA and maybe some of the other space agencies have on the books plans to test a variety of laser-based communications. We've done a few, as I mentioned, like the one to the moon, but there's more to come. Some people have thought that we could somehow get away with using this mysterious property of quantum physics called entanglement, where you deliver, for example, photons to some destination, and then you use the entanglement property and its apparent ability to ignore speed of light delay in order to signal with zero latency. 2 points. The first one is that you still have to get the entangled photon to the destination. You can't do that faster than the speed of light. So there's at least that latency to have to deal with. But the other problem is that entanglement involves essentially correlation. That is to say that if you entangle two photons and you separate them by a significant distance, and then you measure the state of one of them, you automatically know that the state of the other is a complementary state. We've proven this by doing those measurements. Here's the problem. If you had two entangled, that doesn't, by the way, that's not communication, that's correlation. So here's the problem. Suppose you said, okay, I get it. Why don't I entangle the particles, send one of them to Mars, and whatever the latency is it takes to get there, and then force the state of the entangled photon that stayed on Earth in an attempt in the hope of forcing the state of the photon on Mars and thereby achieving a signaling. And the problem is that the entanglement is destroyed by forcing the state of the photon on Earth. And literally anything you do, including measuring the photon, destroys the entanglement. And so unfortunately, you can't use entanglement for faster than light communication. So we're stuck basically using either any electromagnetic form, whether it's high-speed radio or lasers. So that's where we are.
Okay, thanks, Vint. We have a couple more questions. The next one is from Sylvie. He says that any testing with Voyager, which is the furthest space probe we have. Not sure we've done any testing with Voyager, but maybe if we convert the question, what's the most farthest space probe that we've demonstrated DTN capabilities?
So I wish we could do something with Voyager. As you know, it's approximately something like 12 to 13 billion miles away. It's taken it some 33 or 34 years to get there. Unfortunately, we can't reach it adequately to reprogram it in order to test the protocols that way. The farthest away that we've done any tests that I am aware of is 81 light seconds away. You can do the math to figure out how far that is, and that was with the Deep Impact spacecraft from the Epoxy mission. We're likely to do additional tests in near-Earth orbit, which is only a few hundred miles away. We will certainly be doing tests with the moon return, 250,000 miles away. And I have great hopes that in the 2020s, there'll be an opportunity to do some testing again on Mars. I frankly hope that we may have an opportunity to use laser testing. There had been a couple of attempts to do missions that would carry laser test equipment to Mars. One of them was a telecommunications orbiter. Unfortunately, that particular project was defunded, and so we didn't get to try that out. But I know that there is great ambition, and certainly at NASA and in some of the other space agencies, to get testing at least as far as Mars with laser comm as well as with the more conventional radio comm. So that surely will come in the mid 2020s to late 2020s.
Okay, thanks, Vint. Patrick says that, are there any changes needed in the ITUR rules to implement this? I think the question is implementing the IPN is probably the question.
Well, we hope not, and we hope that we've designed this in a way that, in fact, accommodates the need, although we will learn from our live testing and testbed implementation. So when Oscar gives his presentation, I hope he'll be able to tell you a little bit about what we've discovered so far. I'm sure that we will discover that there were things that we didn't think of or did not think through carefully enough. That seems to be always the case. On the other hand, I'm pretty confident that we will have worked out quite a few of any problems from all of the testing that goes on terrestrially in a scaled up, increasingly large scale environment. So I think that the basic protocol design is still aimed accurately. The one place where I still have some real questions, and I'll be haranguing my colleagues about, has to do with the routing through multiple regions. In other words, that if you have a network that gets very big in terms of the number of devices in it, you might need to break up the system into multiple regions. And so inter-region routing is going to become a problem or a challenge, just as it has been in the internet, where we have tens of thousands of autonomous systems, and the border gateway protocol routing system has to accommodate that. Since we aren't using hierarchical addressing, for me anyway, there's a challenge with regard to scaling, and that's something that we'll be exploring over the next several months, at least, in order to reassure ourselves that we have a plan to deal with the scaled up operation. We aren't likely to face anything the scale of the internet anytime soon, but it might be conceivable that we would have a fairly large population of devices in operation in 100 years' time. Even if it isn't people, it might be a number of sensor systems. It might be commercial mining operations on the moon or in the asteroid belt, or other kinds of systems that are populous in terms of edge devices that need this kind of communication capability. So scaling is important to us. The other thing which is going to be a challenge is that multiple entities are likely to be operating pieces of this interplanetary backbone in the same way that there are a number of entities that are operating the internet today. Figuring out what the rules are for autonomy and collaboration and cooperation is going to be very important. And these are areas that we expect the Architecture and Policy Working Group to tackle over time. And so I'm very excited about being confronted with this return to space, because it's forcing us to think our way through what kinds of issues arise with regard to jurisdiction and resolution of disputes, protection of the environment of the planets and the satellites that are in the solar system, protecting historical sites like where we landed on the moon the first time. All of that needs to be considered. We also have to figure out how governments and the private sector work together and still cooperate to protect everyone's interests. So there's going to be a considerable amount of discussion, both within the IPNSIG AWG, the Architecture and Policy Working Group, and also among the space agencies that have already adopted, at least in the interim, something called the Artemis Accords, which dictate the agreement, the ways in which the various entities will work together in a cooperative way on the moon. And of course, those concepts need to be expanded to the rest of the solar system.
Thank you, Vint. I really like how you phrased the very broad spectrum of the challenges we have ahead of us in order to realize this IPN. There is one question in the chat box from Mohammed. Can we use the solution? I mean, I think he's referring to the DTN on Earth for having reliable way of communication in areas where there's no connectivity or bad connection.
So yes, absolutely. In fact, one of the things that excited me about getting terrestrial work going on is that in situations where a disaster has destroyed the communications infrastructure, and for whatever reason we're not capable of building the kind of full and reliable rich connectivity of internet, then having the ability to deal with data that has to be stored until connectivity is restored is very helpful. The same kind of facility is also beneficial in sensor networks where we have battery-powered systems that can't be continuously transmitting and only want to transmit, when there is an opportunity to relay the data to the next node. Or you can imagine a field full of sensors that don't do anything until something comes overhead, as we do in the current Mars situation, where the rovers hold onto their data until the orbiter picks it up. Those all are scenarios that are reasonable in the terrestrial environment as well. So thank you for asking that question, because it's a good reminder that these technologies may turn out to be useful in terrestrial situations in addition to the ones for which they were originally designed.
Thank you, Vint. Since we're running out of time, we have 3-4 minutes left for this event. So I guess I would call that our last question. I think we've gone through all the questions in the Q&A box for the day. So thank you so much. Just a quick announcement on our future events. We will have our next Academy talks on July 13th by Oscar Garcia, who's the IPNSIG board members, and also the lead of the Pilot Projects Working Group. So please make sure you all register yourself. And if you would like to become a member of the IPNSIG, please drop us a note to membership at IPNSIG.org, and our secretariat would be happy to address you. So I would really like to thank Vint once again for giving us such a comprehensive overview on the birth and history of the DTN protocol. More to come, but I hope you all enjoyed the event today. And I guess we will see everyone again on July 13th. Okay.
As they say, see you on the net.
See you on the net. Bye.